all of the physics that we study in this course, even later on, talk about optics, the behavior of light, everything that we discuss always comes back to Isaac Newton. And we know very well the second law, that the net force is equal to the mass times the acceleration. That's Newton's very big deal. That's the equation that makes it possible for me to solve all of these problems. And if you think about it, even though I now have that law of conservation of energy thing, I started that with Newton's second law. I started with F equals ma. That's where the kinetic energy came from. So it all comes back to this. The curious thing about it is that if you go into the work of science that Isaac Newton produced, which is the Principia Mathematica, the big volume of physics that he created, famous work of scientific endeavor, where he did so much stuff, worked out universal gravitation, a whole bunch of stuff about fluid dynamics and optics and all sorts of problems. But the spot where his 3 laws were published for the world, he doesn't really talk about acceleration much. Isaac Newton wasn't particularly interested in acceleration, which is ironic because there it is, F equals ma. Instead, Newton understood that the mass was as important as the velocity. Mass and velocity are different quantities, not just because they measure different things, but the mass is a scalar, the measure of an object's inertia, its mass, and velocity is a vector quantity. So they differ in that way. But Isaac Newton realized that they're both important if you're interested in describing motion. So what Newton preferred to say was the quantity of motion, the amount of motion that a thing has. And be careful, don't think that that's what velocity means, because velocity is the rate of change of the rate of change of position, and there's more to it than that. But it's super simple to understand. Consider this. A freight train, when it moves through our area here, we're sort of in a suburban, urban environment. Freight trains travel quite slowly. You could even encounter a freight train that is moving at a speed that is slower than a person can run. So a freight train could move quite slowly. But a freight train is incredibly difficult to stop. Everyone knows this. You wouldn't get onto the tracks and put your hands out in anticipation of a freight train to lay hands on it and stop it from moving. What happens is you get run over by a train. You can't use your force to stop a freight train. A freight train is difficult to stop, but not because it's going fast. A freight train is difficult to stop because it's massive. A train moves very slowly, but it has a large mass, and therefore it's difficult to stop. So it seems to be about mass. So let me try to stop a bullet, because a bullet has a very small mass. But the way it works is that a bullet has a very large velocity. So the train has a large quantity of motion by virtue of the fact that it has a large mass. But a bullet also has a large quantity of motion and is difficult to stop because even though it has a small mass, it has a very high velocity. You can't stop a bullet. You can sometimes, but it doesn't work out for you. A freight train and a bullet have a large quantity of motion despite having very different velocities, because we should consider the mass and the velocity together. For example, a bumblebee has very little motion. It has a small quantity of motion. It has a very small mass, and it buzzes around with a very small velocity. And so it's easy to stop a bumblebee. Not very threatening, the bumblebees, except for the stabby, stingy bits, but that aside. A bumblebee doesn't have a large quantity of motion. It's easy to stop a bee. If you follow this through logically, there's only one other place for me to go, and that's outer space. An asteroid is spectacularly massive and traveling at stupid velocities through space. And as a result of having a very large velocity and a very large mass, an asteroid is extremely difficult to stop. And in fact, has throughout the geologic history of the Earth had absurd consequences and created extinction events and changes in climate and all kinds of effects from large objects striking the Earth from outer space. And even now, out in our solar system, there are massive objects lurking with huge masses and very large velocities. And astronomers are on the lookout for those things, because if they impact the Earth, it's very, very dramatic, because they have huge quantity of motion. This is what Isaac Newton understood, that changing the motion of objects isn't just about the velocity or just about the mass, or the mass. And Newton's second law does that. F equals ma. The mass is in there, and the change in velocity is in there. We're going to change our thinking a little bit and think about motion the way Isaac Newton would have thought about it. We don't call it the quantity of motion, we call it the momentum. The momentum is a new physical quantity for us, and it's calculated as the mass of an object multiplied by its velocity. That is very simple. That is very, very simple. You just take the mass and multiply by the velocity. No trouble there. But there is subtlety to it. There's always subtlety, right? So let's examine this equation. The symbol for momentum is a lowercase p. You now see why I suggested that you had to have a fancy p for power, because the momentum is lowercase p. Immediately in your head you go, well, why don't you just call the momentum m? I can't call it m because the mass is already busy being m. So we use lowercase p for the momentum, and of course v for the velocity, but the velocity is a vector quantity, meaning it has a magnitude and also a direction. If I'm traveling in the positive direction, I have a positive velocity. If I'm traveling in the negative direction, I have a negative velocity. So that's very easy. We already understand that quite well. And the mass is a scalar, so it has nothing to do with direction. So when I multiply mass and velocity and get the quantity known as the momentum, when I derive that quantity, it's easy to understand its vectorness, which it's inherited from velocity. If I travel in the positive direction, I have positive momentum. And if I travel in the negative direction, I have negative momentum. And it matters to you, the student, positive and negative momentum. It matters because the momentum is going to find its way into equations. Equations that are simple to solve, but equations from which you only get right answers if you respect the fact that the momentum is a vector quantity. Anytime I invent a new quantity, I should probably work out its units. Since the mass is in kilograms and the velocity is in meters per second, the SI units for momentum are kilogram meters per second. And you might guess that I'm suddenly going to say, yes, but we call that a momenton. Just like I said, a joule is a kilogram meter squared per second squared, but we call that a joule. There is no name for the kilogram meter per second. It's a kilogram meter per second of momentum. It turns out that these aren't the units that I use, but we'll talk about those next time, because believe it or not, I've introduced you to this new quantity, the momentum, and I'm done.